The Sparring presentation on the Diffie-Hellman key exchange. This presentation will explain to you how private keys can be generated in a public environment. For example, this algorithm is used in the generation of secret keys when using protocols such as IPsec. Both parties are able to generate a secret key across an unsecure network. This was a major step forward in allowing people to communicate securely across a public environment. Now let's take a look at how this relatively simple algorithm operates. To begin with, the two parties who are going to negotiate the secret key across the network, in this case host number 1 and host number 2, need to agree on a prime number and an integer. In this case, the prime number is 13 and the integer is 6. These numbers can be negotiated across the public network. It doesn't matter if Black Hat or the potential spy is listening in at this point. Next, we need to develop a random secret. Host number 1 comes up with a random secret of number 3. Now this number will never be passed across the network. On the other side, at host number 2, a random secret is also generated, in this case number 10. Again, the number will not be passed across the network. To begin the generation of the first public key, this is the public key which is going to be transmitted across the network, we need to take the integer on host 1, for example, and raise it to the power of our secret, which in this case is number 3. We then take the prime number and we divide it into the result. So we take the 6 to the power of 3 divided by 13. Now notice it's mod 13. This means what we're actually interested in is the remainder from the result. So for example, if I said 13 divided by 4 is 3, the actual answer I'd be looking for with modular math is number 1. So 6 to the power of 3 divided by mod 13, the remainder is 8. 8 has now become the public key. This is transmitted across the network, again in the open, to host number 2. Now host number 2 takes this public key and it raises it to the power of its own random secret. Remember, this random secret will never be transmitted across the network. In this case, the random secret is number 10. We then divide it by the prime, again using modular math, and the result is 12. 12 now becomes our secret key. If we reverse the process and host number 2 does exactly the same piece of math, transmitting its public key across, you can see by looking at the diagram that the same secret key will be generated. Now, despite the fact that a lot of this information has been transmitted in the public environment, the random secrets were never transmitted in the clear. It's extremely difficult to reverse factor these numbers, and that's why we have so much security using the Diffie-Hellman algorithm. Now that we've generated our secret key, let's see how it's going to be used in encrypting our data when we pass it across our public network. First of all, we take the original message in its binary form and we apply the encryption key. Now, applying the encryption key means that we're going to do an exclusive OR with the key and the original message. This will result in our encrypted ciphertext. The encrypted data is now passed across the network to the receiving party. When the data is received, the same key is applied again, and an exclusive OR is performed between the received ciphertext and the encryption key. This reveals the original message. Now, this is at the heart of all encryption processes. However, in the real world, much more complex algorithms are applied on top of this process to scramble the data further, such as the Advanced Encryption Standard, or AES. We can now take a quick look, a high-level overview at how the AES algorithm actually works. This diagram is actually taken from the document which describes the AES algorithm. Here we can see on the left-hand side, in the left-hand block, the data which has been transmitted. The data in the very first round is exclusively ORed with the key. So 32 is exclusively ORed with 2b. The result is then loaded up into another array of memory, 4 by 4. We then look up the position 19 in what is called a substitution table. This is part of the algorithm. And at the position 19 in the substitution table, we find the value D4. For the value BE in the lower left-hand corner, we find the value AE, and so on. Each one of these numbers is replaced from the substitution table. We then rotate all the rows. We shift all the rows. If we look at this block here, you can see the lower row has been shifted 1 position. The next row has been shifted 2 positions. The next row 3 positions, and the next row basically is wrapped around upon itself. After that, we mix the columns, we perform again an additional exclusive OR, and we repeat the process again and again until the data is completely scrambled. And this is basically what's going on at the heart of the encryption standard, AES. On top of that, the key is also being scrambled in each round as well. But this goes a little bit beyond the scope of today's presentation. Thank you for watching this presentation on the Diffie-Hellman key exchange. For a copy of this presentation, you can visit my wiki at allentestwiki.pbworks.com. You can also get a lot more information on Spirent equipment and how we can help you test out your IPsec environments at www.spirent.com. Also, while at the site, don't forget to check out our site to see if there are any live presentations in your area. Once again, thank you for viewing this presentation.